the main intent of this video is to give a detailed description of how a digital control system works. For that, I will be giving a very brief explanation on the working of an analog control system. We'll then move to discrete time domain control system, followed by which we will be seeing the digital control system. Now, I have the circuit diagram of an analog domain controlled buck converter. To start with, we know that the input voltage here nominally it's 24 volt and we should get an output voltage of 12 volt. Most of the time we need to step this down to a lesser value such that it is in accordance with the voltage specifications of this particular transconductance amplifier. So we use a potential divider in most of the cases, and then we step down this voltage. Now we have a reference voltage here, which should be 12 volt typically, because that is our desired output voltage. We take the feedback from here. Since it's a negative feedback, we give to the negative terminal of this transconductance amplifier, and this block is called transconductance amplifier. A transconductance amplifier is very similar to a differential amplifier, except the fact that a differential amplifier will take a difference in the voltage, the input, and then will produce a voltage at the output which is proportional to the difference in the voltage in the input. Now a transconductance amplifier will take the difference in voltages between these two terminals and will produce a current which is proportional to the difference. If the difference in voltage is small, it will produce a smaller value of current. If the difference in voltage is larger, it will produce a large value of current. Now, why is this necessary? Why do we need a transconductance amplifier specifically? Is because we are implementing the integral controller by virtue of a capacitor. Why, if we place a capacitor here, then a transconductance amplifier is necessary? Because this right here is the integral controller. If you take an integral controller, which we will be discussing in very great detail from a different perspective in the upcoming video, now we'll just take the fact that when you take an integral controller, the output should be the integration of the input. When I am giving only when I am giving a current here, this current will be the input to this capacitor, and the integration of that capacitor current over time will give you the voltage across the capacitor, which is the output. So this output, this voltage across it, is the integration of the input. So we need a current to charge the capacitor to produce a voltage across it. That's why we are using a transconductance amplifier. Now this voltage is produced across this capacitor. If you remember the block diagram that we have already discussed in the first video, we would have come across comparator first and error amplifier. Basically that's this error amplifier. Then we will have a controller block. This is our controller block. So what is the output of the controller? It will basically produce a duty ratio. Now this will essentially be our duty ratio. Now having just a duty ratio is not enough. In this case our duty ratio is just a voltage VC, right, which is the voltage across this capacitor. Having that alone is not enough. We should compare it with the sawtooth waveform, which is having the same frequency as your switching frequency. This frequency should be the same as your switching frequency, the sawtooth frequency. Assume that your switching frequency of this whole power circuit is 20 kilohertz, then you have to produce a sawtooth waveform of 20 kilohertz, right? Now, though I have drawn it as a simple sawtooth box, in reality, we will have an analog circuit to produce this sawtooth waveform. Maybe we can use a 555 timer IC to do this. We can connect the IC using certain configuration. We can use resistors and capacitors to obtain a sawtooth waveform. Now this is given to the negative terminal of a comparator, and this is given, duty ratio is given as a positive terminal to the comparator. Now this comparator will in turn produce a PWM. This PWM will be fed to the gate driver circuit. A gate driver circuit, it is necessary for driving this switch with appropriate voltage and current, because all these the ones I have drawn in blue color, are signal level. They may or may not be sufficient to drive this switch. And when I am driving a high side switch, I obviously need some technique in between to drive the switch. So this may be an isolator plus gate driver circuit. You may use an optocoupler or something like that. Essentially, we are feeding this signal into a gate driver circuit, which will in turn drive our switch through the gate resistance and gate to source resistance. Right. Now, moving on to a discrete time domain controller. So this is how a discrete time domain controller essentially looks like. We have the converter in continuous time domain, and we take the output of it. The output of the converter will be something like this. Though this is a slightly exaggerated value, it is almost 12 volt. When we intend to control this system by a discrete time domain controller, we do not take this entire wave as feedback. If you look at the analog controller, whatever voltage is coming here, this V0 waveform, just exactly equal to this whole waveform will be just like the transferred here. However, here, when we are intending to control this system by a discrete time domain controller, we take samples of the output. That's a very great major difference here. So we take samples of output at various time intervals. The general thumb rule is the time interval in which you are sampling, that is your sampling interval, should be equal to your switching period. My switching period here is 50 microsecond because my switching frequency is 20 kilohertz. So this should be the situation here. So I am sampling the output voltage at every 50th microsecond so that I may get a waveform which may look like this. Should be my output, should be time, and instead of getting the whole waveform, I will get only one value here, one value here, one value here, and one value here, and so on. So I will basically sample my output. So there should be a sampler or sampler hold circuit or something in between to convert this continuous domain into discrete domain. Now, why should we take so much of pain in converting this to this? Because you can clearly see that if there is any information present in between this sample and this sample, I may miss it. I may clearly miss it. Similarly, if there is any information or any change in voltage or anything which is happening in between this sample and this sample, I'm clearly missing it because I'm taking voltages only at this time instant, that is only at this time instant, only at this time instant, and so on. I am not getting information about the voltage in all these intervals. So I'm clearly missing some information, right? Why do we do that? It's because when it comes to digital controllers, we have the flexibility to tune it easily. We have the flexibility to reprogram it. We have the flexibility to change any gain or any value as we wish whenever we want, because it's just a matter of changing a line or altering a line in a program. It's as simple as that. It's not as complicated as when you are dealing with an analog control system where the gain of the transconductance amplifier is involved and you won't get capacitor value at whichever value you intend to get. You will get only standard values of capacitor. All these constraints will make your design tedious and it will make it very difficult for you to tune certain values in analog domain. However, in digital domain, you will have the flexibility to reprogram, to alter anything in this happening in this entire closed loop system. When I mean to say a discrete domain digital control system, I mean to say starting from the error computation till the step of producing PWM, if I'm implementing it using a digital controller, then my task becomes easy. But digital controllers work only in discrete time domain. That is the reason why we will take a sample, process it, produce a PWM accordingly, and then we take next sample, process it, produce a PWM accordingly. We do this again and again so as to implement this particular system in closed domain. Now let us look into the details of how this is being achieved. You could see here that I am having the same circuit. The circuit starting from this gate driver here to this entire power circuit along with this voltage stepping down element is the same, is exactly the same as analog. This is the system for us which we want to control. However, the story from here changes. What we're doing is actually we are taking the output after this potential divider, after necessary stepping down, to this analog pin. AX means analog pin. It may be A0, A1, A2, it may be some analog pin, and the ground. We are transferring the output voltage of the converter, stepping down to it by appropriate voltage ratio, and then giving it here. Why do we need to step down here? Assume that I am using an Arduino. In Arduino, you will have the range of this analog pin. The range of this analog pin should be 0 and 5. So the voltage, analog voltage which you are giving to this pin should lie between 0 and 5 volt. What is my voltage here? My output voltage of the converter is 12 volt. So can I feed this 12 volt directly to this microprocessor analog pin? It will damage the pins, it will damage the processor. So we have to step it down using appropriate values of R1 and R2, such that when you give 12 volt here, you will get 5 volt here, something like that. Now, so that's the scenario here. We are going to do something inside this entire digital controller, and at the end, we will be producing a PWM. Here we call this pin as a digital pin or a PWM pin. Digital pin stands for DX, stands for D0, D1, D2, etc. PWM stands for PWM 0, PWM 1, etc. So we have some digital pins at the output at which we produce this. Whenever I talk about a PWM, it's basically a digital signal. Why is it a digital signal? Because it's basically toggling between 0 and some logic level 1. This logic level 1 may be 5 volt in some microcontrollers, it may be 3.3 volt in some microcontroller, doesn't matter. This width is the one which is going to change. Right. Now let us go into detail on how this digital controller works. At the first level, when you give an analog input to this microcontroller, you will have an ADC which will convert this voltage which is lying in between 0 and 5 volt to a mere number. So it will convert this into a mere number because digital computers can work only with numbers, right? So which is technically zero sums. It will convert this output voltage, example 5 volt, into a mere number, which is your output voltage. Just like we computed the error there, we compute the error here. But understand something, computation of error here becomes a very simple process. It's not as complicated as it was earlier. We simply write error equals error equals V reference minus V0. What is our V reference here? 12 volt. So we write 12.0 minus V0. This is the V0 coming out of the ADC. This is our ADC. So error computation is done. this single line of code does the task. Once we compute the error, it should be fed into a controller to produce a duty ratio. That's the next step. You already know it. So we create another block for producing the duty ratio. Now what is this box? This is again a simple equation called as a difference equation. We will look into this in very great detail in the upcoming videos. At the end of the day, it will give you a duty ratio. Now, this duty ratio could be any number. It could vary from minus infinity to plus infinity. But for a power converter, does it make any sense? No. It has to lie technically between 0 and 1, ideally. Technically, it should lie between some 0.2 to 0.8, not even in the extreme scenarios, because the parasitic elements will become dominant when you operate the converter in extreme duty ratios. So we have to saturate it. We have to saturate this duty ratio first, and then with the saturated duty ratio, we have to produce a discrete sawtooth wave and write a condition. This is again a program. Write a condition stating that if my duty ratio is dominant, you produce logic high. If my duty ratio is submissive, you produce logic low. So what is that? It's nothing new. We already saw this. This is my discrete sawtooth waveform. First of all, what do we mean by discrete sawtooth waveform? Discrete sawtooth waveform is something like this. It can count from a value to upper value, then again come down, again it will count to a value, and again it will come down. It will be like this. It's fundamentally a sawtooth. All this will happen because of counting action. It will happen in counter register. So this discrete sawtooth waveform will be generated. And how will this be generated? This will be generated by the use of timers and counters inside your digital controller. Right? We produce this and then we write a logic condition. Again, this is again a piece of code. It's a piece of line. You are writing a if-else statement. If now consider that this is my duty ratio. You are saying if my duty ratio is dominant, produce a PWM, produce logic high. If my duty ratio is submissive, produce a logic low. Again, if my duty ratio is dominant, produce a logic high. If my duty ratio is submissive, produce a logic 0. Now it's again an if-else statement. You do see that all these processes are simply lines of code here. Then we give this to the output. We give this PWM to this pin, according to which it will drive the gate and control the circuit. So this is how a digital control essentially works, and these are all the components which will be present inside a digital controller. So in this, what are the things that we need to focus further is what is this? What is this difference equation? How to implement it in Arduino? How to configure timers and counters in Arduino to make this sawtooth generation happen for your desired frequency. That's one thing, right? And the other thing, we have to understand how this ADC is invoked on a software level to convert this number, to convert this analog voltage to a mere zeros and ones number. How Arduino does it. So these are all the topics which we'll be covering further. So basically there are 3 broad topics to be covered in the upcoming videos, after which we'll be entering the section of programming Arduino.